Welcome everyone to today's virtual AMO seminar. So for those of you that are new, we're taking questions in two formats. You can either enter them into the Q&A of the Zoom, or there's also the chat along with the YouTube live stream. So I'm delighted to introduce our speaker today, who is John Simon, who is the Neubauer Family Professor at the University of Chicago. He got his PhD at MIT with Vladan Vuletic and was a postdoc at Harvard with Marcus Greiner. And now he's going to tell us about fascinating work with twisted cavities and Rydbergs and interacting photons.
Great. Thank you very much, Alicia. And thank you to all the organizers for having me. It's really a pleasure to be here. Particularly under these less than ideal circumstances, it's really nice to have this seminar series to look forward to every week. So before I even get started on the science at all, I wanted to mention very briefly that my talk is going to have two intermissions in it, ideally about a third of the way through, but if you know how I give talks, it could be kind of random. But this will be a nice opportunity to ask questions. You can, of course, ask whenever you want, but don't feel like you have to wait until the end in any way. Okay, so I'm going to tell you about ongoing efforts in my group and in collaboration with Dave Schuster and his group to make materials out of photons. And so before we even get into how to make materials out of photons, I thought I'd start by trying to give you a flavor of what I mean by materials so that when we start to make them, we're speaking the same language. So what I've got here is a simulation of a bunch of little balls. They're shown in blue. They attract each other when they're far apart, and they repel each other when they get close together. And I've added just a little bit of friction. And with just those ingredients, after you wait for a little while, you see that these particles form up into some kind of a crystalline structure. And the point is that this is sort of the emergence of order from simple individual constituents. And what you can see is that the things that we needed were, one, a collection of particles, that is to say, objects with some non-trivial relationship between their momentum and their velocity. We needed an interaction potential between them. And then we needed some kind of a technique to remove entropy from the system. Okay? So this is a classical material. I think it's very sensible to ask in this language what it would mean for something to be a quantum material. Well, what I'm showing you here is sort of a little animation of this crystal. And you can see it has a little bit of motion left in it. You can think of this as kind of like thermal motion, not being in the absolute ground state of the system. But the point is, these are essentially point particles that I've drawn for you at this point. And once they equilibrate in the ground state, they don't move around at all. This is a classical ground state. The thing that gets interesting is if you start to reduce the mass of these individual particles such that the quantum uncertainty in their position begins to grow, you can now have a situation where in addition to the collisions between the particles, they have some quantum uncertainty in where they are, so they can start to become entangled. Okay, and so this to me is what I mean by a quantum material, where there's an interplay of two competing energy scales such that the objects that make up the material can start to become entangled. Okay, so here the competing energy scales are interaction energy and kinetic energy, but it can kind of be any two things that you want. Okay, so to understand this a little bit more formally, I'd like to take a moment to describe something that until fairly recently, I didn't have any kind of a physical intuition about, and that is, what is a collision cross-section? So imagine that I have this green particle here, and then I have a whole bunch of red particles flying past the green particle. So the collision cross-section, which we call sigma, tells you how big the green particle is in terms of how large an obstruction it presents to these red particles. Okay, and so the point is, if the size of the disk that I've drawn for you is the cross-section of the green particle, then it takes a hole out of this set of red particles that's the size of the disk, and those particles fly off in other directions. So this gives us sort of a new way to think about these collisions. If instead of thinking of these this red disk as a bunch of particles, we thought about it as one quantum mechanically delocalized particle, you can look at the collision probability as the size of that particle, the area over which it's delocalized, compared to this collision cross-section. Okay, so this leaves us again in a pretty interesting position where we can say if the position uncertainty of an object is much smaller than its collision cross-section, then you should think of it as a classical particle, sort of a point particle type object. On the other hand, if the object's position uncertainty is much larger than its collision cross-section, then classically we would think of this as a wave. And this should give you some intuition, I think, as to why normal matter, baseball, marbles, these sorts of things behave as particles. A marble has a position uncertainty associated with its very large mass. And so that position uncertainty is very small. And its collision cross-section is sort of set by this physical size of this whole glassy structure. Okay, so its cross-section is large, its position uncertainty is small, it behaves like a particle. On the other hand, light, photons basically don't interact with each other, but they do have very large position uncertainty on the order of their the wavelength of the light or larger. And this is why light sort of normally behaves like a wave. And this now leaves us in a really interesting position because we're used to making materials, that is to say, emergent structures of objects out of these sort of particle-like things. We take things that essentially don't have wave properties in the sort of classical limit, and we cool them down until the quantum uncertainty of their position starts to become comparable to their separation, and we see how they order. Okay, this is in some ways, I would say, the cold atom approach to making materials. What I want to tell you about today is making materials out of things that classically look like waves, and then sort of turning up the interactions between those things until the photons start to order. And what you'll see is that in addition to this challenge of making photons interact, there are a bunch of other challenges that point to some really beautiful and interesting physics. So one of the sort of central challenges here, one is that forces don't slow down photons. So why is this an important challenge? Well, if I want to make a material out of, say, massive particles, I can imagine a particle that's moving to the right, and I apply a force to it to the left. The particle slows down and then moves back to the left. On the other hand, if I take a photon, here shown in blue, and I have it moving to the right, and I apply a force to the left, well, the photon changes color. It didn't slow down, it just changed color. And when you make materials, it's really much more useful when objects collide for their momenta to change rather than their color to change. I guess you could imagine some kind of a material model, maybe it'd be more like a spin model where the color changed, but we would like forces to slow down and speed up our particles. So why do photons not slow down when you apply forces to them? Well, it's because the relationship between their energy and their momentum is linear. And what you know is that the group velocity is sort of the partial derivative of the energy with respect to the momentum. And since that relationship is linear, there's just a constant velocity. And so what we're going to need to do to make our photons act like massive particles is trap them in some kind of a metamaterial where we can change their dispersion so that they effectively have some mass. Okay, so that's step one. How do we give photons a mass so that they can have any velocity that we want? Step two is that if you have two electrons and you let them come towards each other, they can collide and bounce off of one another. But we know from Maxwell's equations that if I have a solution for a wave moving to the right and a solution for a wave moving to the left, well, if I add those two waves, the solution is the sum of those individual solutions. The waves don't interact with each other. Maxwell's equations are linear. Photons essentially don't interact. You know, we don't, for the most part, live in the Star Wars universe as much as we like to believe we do. So how can we make photons collide? We'll take a little bit of inspiration from electrons. Well, what we know is that in quantum electrodynamics, electrons really collide by exchanging virtual photons. So you might say maybe we could make photons collide by having them exchange a virtual electron. Well, this Feynman diagram is disallowed by everything. And so we need to come up with some other way to make the photons collide with each other. It turns out there's this fancier Feynman diagram which is allowed, but the collision cross-section for this process is extremely small. Remember, we just defined collision cross-sections. This says if you thought of your photon as a marble that other photons were going to try to collide with, how big would that marble be? And it would have a radius of like 10 to the minus 28 microns, which is very, very small. That's not going to be useful for making the photons collide, because remember, the diffraction limit sort of means we can only focus photons down to order of a micron, and we're 28 orders of magnitude away from where we need to be. So that's not going to be good. But the interesting thing here is that the reason this collision cross-section is small at some level is that the energy of these photons is very small compared to the energy of the electron-positron pairs in the middle of this Feynman diagram. So if we could do the same kind of thing, but mediate the interaction between the photons with atoms and do it resonantly, we'll be able to make much stronger interactions between our photons. And in fact, we'll be able, for our optical photons, to have one photon to have a cross-sectional area of hundreds of microns squared, which is almost as large as a human hair. It's quite surprising. Okay, so we've now more or less gotten through the introduction, but I did want to point out just quickly what the real analogy is that we're trying to build on here. So in the solid state, materials are made out of electrons that interact with one another through the Coulomb potential. And they have a bare mass in vacuum, but when you trap them in the crystalline lattice of a solid, that changes sort of the effective mass of the electron, changes the dispersion of the electron. Much of the work in the AMO community has gone to making optical lattices for cold atoms, where the atoms interact with one another through sort of van der Waals interactions usually, and their effective dispersion is set by this lattice potential. What we're going to do is make materials out of photons. Okay, and so the photons will interact with one another by having them, that interaction mediated by matter. And then we will trap the photons in some kind of a metamaterial that will give them dispersion. And the key is that this metamaterial here has to be very, very low loss to ensure that it doesn't absorb our particles before they can collide with one another in order. Okay, and so the two stories I'm going to tell you going forward, time permitting, are one about making materials in the continuum out of optical photons, where the collisions between the photons are mediated by Rydberg electromagnetically induced transparency. And then a second story focusing on circuit quantum electrodynamics, actually, where the particles that interact are microwave photons. They are trapped in arrays of superconducting resonators. So this is more like lattice physics. And the interactions are mediated by transmon qubits. Okay, and in each case, what I really want you to try to take away from this is how we make photons behave as particles, that is to say, how we control their dispersion, how we make them collide with one another, and what the techniques we're using are to assemble few to many body states. So with that, we have reached the end of the introductory third. And so I think now is as good a time as any to take a few questions if there are any.
Okay, so I guess I'll be asking the questions, and again, I want to encourage you to use the question box on your Zoom link, and there's also a place for you to add questions in the YouTube stream as well. So we'll be collecting those as we go along. But let me ask a question of my own, John. I guess I see that making quantum matter out of photons is a very appealing challenge for the sort of the new quantum era. But what kinds of materials do you think can uniquely be created only by photons?
This is a great question.
Of course, it's a great question.
And you're a great person, Dan. So I think one of the things that makes photons quite unique for making materials is that, as you may be aware, they move really fast. They move almost at the speed of light. And so to make a material out of them, we're going to have to come up with techniques to kind of slow them down by trapping them in something. But what this means is that at any time we can kind of let them leak out of our system and leak back in somewhere else. And that looks almost instantaneous, okay? And so what this means in practice is that you can make models with all kinds of long range and non-local couplings that are very hard to realize in any other kind of model. I'm not really so focused on that today. I'll probably touch briefly on this idea of having photons on curved surfaces. And one of the ways that we engineer these sort of curved spaces for the photons to live in is through this non-local hopping of the light. So that's one piece. The other thing that I would say that's sort of unique and nice for photons is that we're very good as a community at engineering the electromagnetic vacuum, engineering the electromagnetic density of states. And so what this means is that you can use reservoir engineering techniques, thermodynamic manipulation techniques to cool systems of photons in ways that are potentially challenging for making materials out of cold atoms or even out of electrons. So we'll see that a little bit on the circuit side, but this basic idea of engineering the density of states for the particles that exist in your system, which is what I'll show you for the making magnetic fields for light, and then for engineering which states decay quickly, which states we inject, these sorts of things, I think is also quite exciting. So, can I proceed?
There's also a question from Said Pegahan about what is the, let's say, coherence timescale that would be required in the system in order to study the entanglement or material properties that you are searching for?
Mm-hmm. So this is a really interesting question. If I had to compare them, which question did I like more? I probably like Said's question more. No offense, Dan. Yours was good too. So I actually skipped this slide for this talk, but I would say fundamentally, the thing that you have to ask is how many collisions can you have between your particles before a decoherence event occurs? So for a cold atom, this would be the atom scatters a photon or is hit by a background gas particle and knocked out of the lattice or something like that. So the idea is every time the particles collide, they get a little bit entangled, okay? And you just have to make sure that you can have many collisions before you lose your particles, in this case, before the photons are absorbed either by the walls or leak out of the cavity or something. And so these numbers, you essentially have to make bigger than unity to see any entanglement at all, and how the quantity of entanglement scales with the number of collisions you can get within the lifetime of the particles depends very sensitively on the model that you're studying. And so I think if you want to talk about that more, Said, we can talk about it afterwards, but that's a great question. Okay?
Okay, let me throw out another question. Skylar Kane asks that you're talking about materials that are made of photons, but also suggesting that the interactions come about mediated by massive particles.
Mm-hmm.
So is it clear when the material should be understood from looking at the properties of the particles that are the force carriers versus the properties of the photons?
And this is, so again, I would say this is philosophy. I think the reason I made the analogy to making electronic materials is that, you know, electrons interact through photons, but we don't talk about those materials as being made out of photons. And so maybe the counterpoint people make there is that those photons are off shell, they're only virtual. And our atomic excitations will actually be more or less on shell. So maybe you should think of our materials as consisting of photons that are sort of a little bit glued together by the atoms. I'm fine with that. So shall I change the title? Making matter out of matter and light. It's a good question.
I'm the one asking the questions. And then let me ask the last question on behalf of Bill Phillips. He is pointing out that often when we talk about quantum collisions, we make a comparison between the range of the potential and something like a scattering length or the square root of the cross section. You're suggesting that we instead have a different comparison scales to determine sort of when quantum happens. Can you talk about the relation between those?
Ooh. That is a really good question, and I don't know that I have a great answer off the top of my head. Maybe we revisit that at the end. I wish I had a good answer to that question, but I just really don't.
Okay, I'm going to suggest we let you continue. Thanks.
Great, thanks, Dan. Okay, so let's talk a little bit about making topological materials from optical photons. Okay, so the start of this story is that photons in an optical resonator act like massive particles in a harmonic trap. So what does this mean? Here I've drawn two resonator mirrors in blue. And what I'm claiming is that if I inject light into this resonator, it'll oscillate back and forth in this vertical direction, like a massive particle in a harmonic trap. So we can start to understand that in a ray optics picture, just watching how the ray moves back and forth. And we're just interested in how it collides with this middle plane of the cavity. And what you can see is this really looks like the stroboscopic evolution of a massive harmonically trapped particle. Okay, so we can be a little bit more formal about this, and we can say that this photon now has a transverse momentum, which is proportional to the slope of the ray relative to the cavity axis. Okay, and the neat thing is that on a round trip through the cavity, the distance that the photon moves in this transverse direction is proportional to that transverse momentum. And so what that means is that this photon can now have any velocity that we want. And indeed, this relationship between the transverse momentum and the transverse velocity gives this photon what I would call a transverse mass. Okay, and the other thing that you can see is that the curvature of these cavity mirrors prevents the rays from just kind of bouncing forever and just moving upward ad infinitum. And so this corresponds to harmonic confinement. Okay, so this is sort of in the particle picture how you should understand this physics. We can also ask in a wave picture what's going on. Well, the deal is that in a wave picture, a harmonic oscillator has eigenmodes that are Hermite-Gauss in space and uniformly spaced in energy. Okay, and in fact, if you just compute the modes of a two-mirror Fabry-Perot cavity, they are also Hermite-Gauss in space and uniformly spaced in energy. So as a consequence, you can see that there's not just kind of a qualitative analogy between these two systems. Photons in a multimode optical cavity really have dynamics that's essentially mathematically equivalent to this massive harmonically trapped particle. So just to really put the nail in the coffin here, so to speak, if I sent light into this cavity offset to the right of the middle of the resonator axis, I can write that as a superposition of this lowest transverse mode and the first excited transverse mode. They'll interfere constructively on the right side of the cavity and destructively on the left side of the cavity. But the neat thing is that they're evolving at different frequencies by this transverse mode spacing. So half a cycle later, this plus sign has become a minus sign, and now the photon is offset to the left side of the cavity axis. And so the picture you should really have in your mind here is exactly the same as the reason why a coherent state oscillates back and forth in a harmonic trap. So again, to give you a visual here, these are two mirrors, and the light is delocalized everywhere along the cavity axis. We're thinking of a single longitudinal mode of the cavity and many transverse modes that add up to a wave packet that oscillates back and forth like a massive particle. Okay, so great. We've got a pretty simple story. Then the free propagation of the light gives the photons mass, and the mirror curvature traps them in this transverse direction. So one might then be inclined to ask, can we make the only other interesting quadratic term that can exist in such a system, which is xpy minus ypx, a magnetic field. And what we're going to find is that by twisting the resonator, we can actually do that. Okay, so to understand why twist gives a magnetic field, the picture you should have in mind is a periscope. If I look at this little tree through a periscope, it starts out vertical, it comes out vertical at the bottom. If I rotate the top mirror of the periscope by 90 degrees with respect to the bottom mirror, the tree started out vertical and came out horizontal. And so the basic idea is that as I rotate this top mirror relative to the bottom mirror, I can get any rotation of this tree that I want. And so if I just add 2 more mirrors to this cavity to close the loop, then on each round trip, if I can generate a twist of the rays in the plane. So the idea is now on each round trip, the propagation was giving us a photon mass. The curvature of the mirrors was giving us harmonic confinement. And now the twist of the cavity turns the lab frame into a rotating frame. On each round trip, not just the polarization, but the whole light image gets rotated through some angle. And what we learned in high school is that when you go into a rotating frame, you get Coriolis and centrifugal forces. But for us, these exist in the lab frame. So they're not fictitious forces, they're real forces. And this Coriolis force looks like omega cross P, which indeed is the same as V cross sum B. So we've got this Lorentz force that we need. And the centrifugal force is just a force that's radially outward that increases the further you move from the cavity axis, and which is the same as sort of living on an upside down harmonic trap. So we can just add mirror curvature to get rid of that, okay? So, and that will leave us with just this Lorentz force. So what will that look like in terms of the mode structure of the cavity? Well, here we have a 4-mirror cavity in the plane. And so the way you should think about this is it's like a 2D quantum harmonic oscillator. It has a lowest mode. It has 2 first excited modes, one that's excited along X, the other is excited along Y. It has 3 second excited modes and so forth. Now, when I twist this cavity out of the plane, these can no longer be eigenmodes because under a round trip, the image gets rotated slightly, okay? And so as a consequence, it's not an eigenmode if it doesn't stay itself. So we need to make some superposition of these 2 modes that is invariant under rotation. That's a ring. And indeed, this X mode plus I times the Y mode or minus I times the Y mode will give me rings. So as I start to twist this cavity out of the plane, all of the modes will become rings. And we can identify this lowest family of modes with the lowest Landau level. And when we talk about Laughlin states in a little while, we will need to know the mathematical form of the wave functions in this lowest Landau level. So let me just point those out to you quickly. They're indexed by this index L, which is 0 for this first mode, then 1, 2, 3, 4. And then I write them in terms of a complex coordinate Z, which is X plus IY or R e to the I theta. And the nicest way to write this mode is basically Z to the L e to the minus magnitude of Z squared, which you can see when I write it in polar coordinates is R to the L e to the minus R squared times this e to the I L theta. So the e to the I L theta means that the Lth mode has angular momentum L times H bar. Okay, and the R to the L e to the minus R squared just moves the ring outwards more and more the larger L is. Okay, so we build this object experimentally. The first time we did this, we just 3D printed a little plastic structure and stuffed 4 mirrors into it. We looked at the mode of this thing and we get these beautiful rings. We can be a little bit more formal about this and look at the energies of these modes as we sort of vary the length of the cavity, which is sort of a proxy for the twist. And we can find this point where all of the modes look essentially degenerate, all of the modes of this lowest Landau level. And you can see that they're degenerate to within about 1 megahertz. And this is going to be really important going forward, because that means if we can get interactions between the photons that are stronger than 1 megahertz, they will be able to rearrange themselves within this family of degenerate modes to build an ordered state. Okay, so there's a whole nother set of stories studying the non-interacting physics of these individual photons, where we measure their Chern numbers, we measure Chern markers, we explore how they move around in this lowest Landau level. But I promised you today that we were going to talk about how to make these photons collide with each other in order. So let's hop over to that. So we've got ingredient number one. We've learned how to give the photons mass and how to apply Lorentz forces to them. How do we make them collide? Well, imagine I have photons moving in free space, okay? And I'm going to send them through this atomic medium here, shown in blue. What you should have in mind is that when this first photon enters the medium, it slows down. Why does it slow down? Well, because the photon is absorbed by one of these atoms and excites the atom to this 5p3 half state, from which the atom is then excited very quickly up to a very long-lived Rydberg state. And for what I'm telling you right this second, the only thing that matters is that that state is very long-lived. The fact that it's long-lived means that the photon can slow down, because essentially the photon isn't a photon when it's absorbed by one of the atoms in this medium, and the atoms live for a long time in that excited state. So the light can now propagate through this atomic cloud very slowly. But here's the interesting thing. If a second photon comes into the medium and tries to get near the first photon, what you discover is that these two Rydberg electrons can now interact with each other strongly. We work with like the 111D state of these Rydberg atoms, so they can interact over tens of microns. And so what that means is that this Rydberg level here gets shifted in energy if the second photon comes near the first photon, and the light then does not move slowly through the cloud. And what I'm depicting here with the color gradient is that if this red photon is near the black photon, it moves quickly. And if it's far from the black photon, it moves slowly. And so this really looks like a lens. So this second photon lenses off of the first photon, and you can really think of this as collisions between these two photons, okay? This is in some ways a generalization of ideas developed by Misha Bladen, Charles Adams, Alex Kuzmich, and others for free space Rydberg EIT. What we do is related experiments, but now we have the photons in a cavity. And so you should think of these photons as delocalized along the cavity axis, oscillating back and forth in their harmonic trap, but now they spend part of their time as atomic excitations. And indeed, in our case, they spend about 90% of their time as atomic excitations. So what does this look like in an experiment? We load a magneto-optically trapped sample of atoms into a 1D optical lattice, transport those atoms into a 4-mirror cavity, and then you can look at an actual absorption image of these atoms with the cavity mode drawn through here for scale. And so we now cool these atoms in an elliptical trap until they're only about 10 microns thick and 100 microns across. We choose this 10 micron number because the atoms can interact with each other in this longitudinal direction over about 10 microns. So this atomic cloud essentially looks two-dimensional, okay? So now we can start to do experiments in this system, okay? So the challenge is that these photons are put into a single mode cavity to build the simplest possible example for now of how this physics might work. So if you look at the transmission of this cavity in this single mode limit, it's essentially like a zero-dimensional quantum dot, okay? So for those of you who are experts in cavity QED, these outer two peaks are what are typically referred to as vacuum Rabi peaks. They're a superposition of an atom in the P state and an atom in the ground state. I can see Alicia leading forward, probably because these peaks are very, very tiny, and I agree, they're very small. But the thing that's interesting here is that this middle peak is much narrower and much taller, and that's what we call our cavity EIT peak. And this peak can be narrow because the Rydberg state is very, very long-lived. So when we send photons in at this energy, we're creating excitations of this cavity system that are part optical photon and part Rydberg excitation of our atomic cloud. So this cavity is about 6 centimeters long. And the idea is now that if we send light into the cavity at this energy, the cavity can hold one photon, but if we try to send a second photon in, the repulsion between the photons prevents it from entering the cavity until the first photon leaves, and only then can a second photon enter. And so the way you should understand this macroscopic 6 centimeter long device is that it can only hold one photon at a time. And the way we characterize this is by looking at when one photon leaves the cavity, what's the probability that another one leaves either immediately before or immediately after. And you can see that we get almost perfect suppression of 2 photons leaving the system at the same time, meaning that the system really couldn't hold 2 photons simultaneously. So great, we've got our 2 ingredients. We've got a magnetic field for light. We've got strong interactions between our photons. What we need to do now is explore what happens when we put these 2 ingredients together. So I'm going to zip through this fairly quickly. If you want the details, you can take a look at this archive manuscript. But let me start by giving you a qualitative picture of how this should work. And this comes from a proposal by Jacopo Carasotto and Onur Omokalilar, which is really quite beautiful, and I think tells you a lot about topological few to many body physics. So I've separated these states of the lowest Landau level out in energy for clarity, and I've written down their wave functions here just as a little reminder. The experiment I just showed you, imagine that we only had access to this lowest state of the lowest Landau level, and that we shined light into the cavity. And what we saw was that we could put one photon in, but a second one couldn't enter because the photons interact with one another strongly. Okay, so that's this blockade effect, originally demonstrated actually by Jeff Kimball with a 2-level atom in a single mode cavity in 2004. What I'd like to ask you is what you think happens when I shine light on the cavity that excites this L=1 mode with some angular momentum. Well, you might think those photons still interact with each other, so there should still be a repulsion that prevents me from putting 2 photons into the cavity. And at some level, you're right, but there's now a new process that can happen, which is that these 2 photons can actually collide and rearrange themselves in space, okay? These collisions can take 2 photons, each with 1 unit of angular momentum, and turn them into 1 photon with 0 unit and 1 photon with 2 units of angular momentum. And that conserves both energy and angular momentum, so this is an allowed process. So now you have to ask, is there blockade or isn't there blockade? Is there some superposition of 2 photons with 1 unit of angular momentum, or 1 photon with 0 and 1 photon with 2 units that doesn't have any interaction energy, so it can actually go through the cavity? And it turns out there is. Laughlin got a Nobel Prize for describing this state in the context of electrons. Let me just write down the wave function for you, and we can try to understand the connection. So this wave function is a function of 2 variables, Z1 and Z2, which are the positions of my 2 photons. Okay, and the idea is when Z1 is equal to Z2, this wave function is 0. So the photons avoid each other in space. I pay no interaction energy. So that's great. The other thing that's neat, though, is that this state lives within the lowest Landau level. How can we see that? Well, we just expand out this quadratic, and I get Z1 squared Z2 to the 0 plus Z1 to the 0 Z2 squared minus 2Z1 Z2. Okay, and now we can identify the terms here with terms in this lowest Landau level wave function description, and draw this state as kind of a superposition of the first photon with 2 units of angular momentum, the second with 0, and so on and so forth. And so the point is, there is a superposition of these 3 states that has no interaction energy. And if we send light through the system, what we expect to see then is that pairs of photons can come out essentially without having to pay any interaction energy, as long as they come out in this Laughlin state. So we send them in with L=1, and pairs come out entangled in this Laughlin state. So what does this look like in the experiment? We generate our photons with angular momentum using a DMD. we have a twisted cavity with these Rydberg dressed atoms inside. And then we have an array of cavities to sort these photons by their orbital angular momentum when they leak out, and let them kind of scatter through this system. So just as a reminder, for this single mode cavity, the interactions meant that only one photon could go in at a time. But what we expect for the multimode cavity is that the photons will be able to go in to some extent 2 at a time, but they'll have to rearrange themselves in space. And so what that means is if we look at all of the photons coming out, we do actually see that there's a little bit of suppression of 2 coming out at the same time, but not a complete suppression, meaning that the photons are able to reorganize themselves and make it through the cavity. Note that we're using states with angular momentum 3, 6, and 9 instead of 0, 1, and 2. That's for technical reasons that we can talk about after the talk if you'd like. Okay, so we can actually characterize what the angular momenta of the particular photons leaking out are by looking at their correlation functions in time. And what we see is that there's some increase in the rate of pairs of photons with the same angular momentum coming out, but the main reason that we're able to see pairs leaking out is that when we get a photon with 9 units of angular momentum, it almost always has a partner with 3 units of angular momentum. That is to say, these photons are really colliding in self-ordering. Okay, so these are the amplitudes that we measure for pairs of photons in the initial state versus these collision products. And you now have to ask, what is the relative phase between them? Is there a relative phase between them? And the way you measure that is to note that the whole reason this state should have existed in the first place was so that the photons could avoid each other in real space rather than in angular momentum space. And so what we essentially do is measure locally somewhere in the system in real space and just watch as the photons come out and see if they're anti-bunched. Okay. And there's a complication because this cavity is twisted, so the whole state is kind of rotating in time. But the upshot is that the photons avoid each other at 0 time. Half a cycle later, they're bunched, and then then another half cycle later, they avoid each other again. Meaning that if you look at just a particular point in space, you can get all of the information as the state rotates around you. Okay, so the state that we've built is this Laughlin state that I've written here. If you want to be very formal about it, it's a 2-photon Laughlin state on a cone with a quasi-hole at the origin. So this is normally where I would have another little intermission. Now we're just going to wait long enough for Emmy to yawn. And I think I will go ahead, Dan, with your permission, to just give people a flavor of the second system, or would you like me to answer a question or 2 here?
How much more do you have, John?
So probably about 6 or 7 minutes.
Okay, let me have you just get to the end. We'll ask all the questions at the end.
All right. So just very briefly, the other thing that I'm excited to tell you about is that you can, much as we in the cold atom community study different species of atoms to get access to different kinds of physics, you can kind of do the same thing with photons. Looking at photons of different frequencies, you can make materials out of them as well. So I'd like to tell you just very briefly about making materials out of microwave photons. So here we're going to work in lattices. So what's a great lattice site to hold a microwave photon? It's an LC resonator. So this resonator has a resonance at some frequency 1 over root LC. We're going to set that to say 4.5 gigahertz. So this LC circuit is a box that holds 4.5 gigahertz photons. It can hold 0 of them. It can hold 1 of them. It can hold 2. But the point is, if you want to think in the language of Hubbard U's, because the first photon is 4.5 gigahertz and the second photon is also 4.5 gigahertz, this lattice site has a Hubbard U of 0, right? So these are not interacting photons. But you can do something neat, which is you can replace this inductor with an inductor whose inductance depends upon how much current is flowing through it. You could imagine doing that by having a situation where the inductor just heats up And when it heats up, its shape changes, that changes its inductance, and now you have a current-dependent inductance. Well, that works perfectly, except that for any kind of a reasonable inductor, you need to put, moles of photons or moles of electrons through it to get it to heat up much at all. So we need something very small if we want it to heat up. But in fact, if we make it as small as possible, just a little tunnel junction, you find that there are other more interesting quantum mechanical effects that give you a current-dependent inductance. So you should now think of this circuit as a capacitor and a Josephson junction as an LC resonator, but it's a nonlinear one, okay? Where if you put one photon into this circuit, it basically has an energy of 4.5 gigahertz. But if you try to put a second photon into the circuit, it's now going to have an energy of 4.2 gigahertz, meaning you have about 300 megahertz of attraction between these photons. So that's great. We've got our Hubbard U. What if we want to have tunneling between our sites? Because that's usually the other quantity we need to make a material, right? We need interactions on site competing with a kinetic energy term. So why do we call this circuit quantum electrodynamics? Because you can just couple the lattice sites together with capacitors, and now you can generate a tunneling of whatever energy you want. In the circuit I'm going to show you, our tunneling energy is about 10 megahertz. So just to get a quick summary of our numbers here, our interaction energy is about 300 megahertz. Our tunneling energy is 10 megahertz. We're deep in the strongly interacting sort of Mott regime here. And our photon lifetime is 40 to 100 microseconds, meaning we can get like 12,000 collisions or 400 tunneling events rather within the lifetime of a single one of these photons, going back to Saeed's question at the beginning. So the neat thing though is that this circuit that I just described to you realizes these 4 lattice sites, but it doesn't make a Mott insulator because we haven't put particles into the system. So in the cold atom game, what you do is you'd first turn off your lattice, you'd laser cool atoms, and then sideband cool them, then evaporatively cool them into a Bose-Einstein condensate, and then turn a lattice on slowly and adiabatically prepare the ground state. So that would require adiabatically tuning these capacitances and so on and so forth, which is possible with the circuits, but not so pleasant. I'd like to give you a different approach, which is in line with these quantum thermodynamics ideas that I was mentioning to Dan in response to his question earlier. What we need to do is make a device which can give photons to our system, but only photons of this particular energy, and it can never take photons back. So if we had that device, we could put a first photon in, and then this thing would refill itself, and it wouldn't be able to put a photon into the system because the second photon would have to have a different energy until that first photon moves, and then the second photon could enter, and then this would refill itself, and so on and so forth, until we've filled up the whole system. It turns out this kind of an approach works whenever the many-body system that you're trying to stabilize has an incompressible phase. That is to say, you put particles in, and it wants to take particles more or less of the same energy until it fills up to its compressibility gap, and then it can't take any more particles. So the Mott insulator is an example of this. Fractional Chern insulators can be examples of this. There are many such examples. A superfluid, though, is not an example of such a phase. Okay, so how do we make this object? Well, I've told you how to make these guys. They're basically these capacitors shunting Josephson junctions. We've got readout resonators to look at the occupation of each lattice site. And now we just have to figure out how to make this object. And we can actually take our inspiration from cold atoms. What we would like to do is have one lattice site that we always invert and optically pump into this one photon state. So how do we do that? Well, we can't just continuously excite it from 0 photons to 1 photon with a microwave tone, because once it's excited, that same tone will de-excite it. In the same way that you cannot invert a 2-level atom, you have to use this 3rd level. So what we're going to do is need fast decay of this 2-photon state, which we will achieve by coupling this qubit to a RLC circuit, which is tuned to this particular resonance and has a resistor to absorb these photons very quickly. And then we will excite the system from 0 photons to 2 photons with just a microwave drive, okay? In fact, you can think of this very much analogously to evaporation in a cold atom experiment. The point is you have a pair of atoms, they can collide One of them goes up above your RF knife and gets evaporated, and the other one loses energy and goes down in your harmonic trap. So these kinds of ideas exist, but perhaps not so much in the strongly interacting regime that we're realizing. So let me just show you what the result is here when we do this. This figure on the right, I'm showing you the occupation of each of our 7 lattice sites. The refilling site is at this end, and time is going to be in the vertical direction, not in the virtual direction. It will be in the real vertical direction. So if you just watch, the system fills up over a few microseconds to 1 particle per site. We've really built this mod insulator, and you can now even see that there's some kind of a Lieb-Robinson bounded filling front here, and so forth. You can ask what happens if we remove a particle from the system. If this refilling is not on, we get a quantum random walk of a hole. And if the refilling is on, the hole random walks until it gets reabsorbed. And that's the way you should think of this dissipative stabilization idea in general. Once you've got a mod insulator, whenever you lose a particle, it random walks back and forth through your system until it gets to this site where it can be reabsorbed and the many body state can be corrected. So looking ahead, we'd like to kind of combine these ideas, dissipatively stabilize optical photons instead of microwave photons, explore how entanglement evolves in these thermalizing systems. We have thoughts building on ideas from Misha and Eugene on how to braid anyons using impurities, and so on and so forth. But I think at this point, what I really ought to do is just stop. I do want to thank my group though, and in particular the people who did the hard work to make this science happen. On the circuit side, that was Alex Ma, Brendan Saxberg, and Dave Schuster, the group leader, leading the circuit side of the work. Gabrielle Roberts is a new member of that team and doing wonderful science. On the optical photon side, this work has been led by Nathan Shine and Logan Clark, and it's now led by Claire Baum, Lucas Palm, and our fantastic postdoc, Matt Jaffe. So thank you all for your attention.
Thanks for a great talk, Don. Maybe I'll forward some of the questions. So let's see. This is about back to the optical part. Bill Phillips asks about concerning the degeneracy of the lowest Landau-Levels. Is this degeneracy achieved like in a confocal Fabry-Perot cavity where you adjust the mirror spacing to make the modes degenerate?
Yes.
Okay, and then related, Alan Chu is asking what defines the number of degenerate states when you now isolate just, let's say, 3 of these lowest levels. So how do you achieve this isolation just to the, I guess, the 369 or the 036?
Mm-hmm. So that's a wonderful question. I've swept some complexity under the rug. To get the cavity waist small enough for our early cavities, the one that I showed you for this Laughlin work, that the photons can interact, we ended up in a situation with a fair bit of aberration. And so what that ends up meaning is that when you really make those modes degenerate, the cavity becomes still slightly unstable for some sort of subtle and complicated reasons. So what we do to keep things simple here is we actually tune the modes away from each other. And then we put sidebands on the atomic P state to have it be resonant with the 3 cavity modes that we're interested in. Okay, so the cavity modes are separated by 70 megahertz. And what we do is we shake the P state of the atom up and down at 70 megahertz, such that the P state lives at multiple energies separated by 70 megahertz. And that gives you effectively a degenerate system for those 3 modes. And if you shook it harder, you could have more modes be degenerate, but we actually only want those 3 to be degenerate for now.
Wonderful.
Really
Returning
cool
to Bill Phillips, he's wondering with this sending in, let's say, a coherent state and spitting out a Laughlin state, should I think of that as being some sort of filter that's applied to the optical input that sifts out Laughlin states from an uncorrelated input?
Yes, that is exactly how to think about it. And based on that argument, you can see that that approach is not going to work well as you go to more and more particles, right? Because like, what's the overlap between, say, 10 photons with L equals 10 and a 10 photon Laughlin state? Work from Mohammed Hafezi and Misha and others suggest it's like 1 over n factorial. And as you may be aware, factorial is scales very poorly. So that's why these dissipative stabilization schemes, I think, are much more favorable in the large system size limit. I think this light on my face really makes me look a little bit angelic. I hope you guys are all enjoying that. Dan's not even going to react to that.
No more than usual, John. I have a question also from Joe Whalen about the anti-bunching signal. So what sets the size for the hole that you see in the G2 function? And also in both of the G2 functions that you presented, there was an excess above 1 when you moved outside of the hole. So what causes that later bunching of light, or those correlations?
Okay, so let's go back up here. So he's talking, I guess, about this and the fact that it goes a little bit above 1 there.
For example.
Yes. Or are we talking about this average level? The average level piece is very easy to understand. I'm not sure that the overshoot here is even so real. We can talk about that. But the fact that the G2 at long times goes to like 1.1 or 1.2 is a pretty common thing in these sorts of systems. Imagine that your atom number is fluctuating a little bit. The point is that when the atom number fluctuates up, this peak maybe gets a little bit narrower. So it takes photons longer to come out, fewer of them make it through your system. Okay, when the atom number fluctuates down, this peak gets a little wider and a little taller, photons make it through more quickly. So what that means is that detecting a photon, in addition to telling you that the system can only hold 1 photon at a time, when you detect a photon, it's more likely that there were fewer atoms than that there were more atoms, right? Because more photons come through when there are fewer atoms. And so what that means is that you've generated a positive correlation on the, at least until the atom number fluctuates back down at long times. And so what that can come either from random fluctuations or a little bit of atomic decay over our 100 milliseconds of data collection. But we consider this 1.2 to be 1. Yeah. So you're wrong. There's nothing to see there.
Okay, thank you for emphasizing the precision end of our field.
Exactly.
Let's see. Aruku Senu asks whether you have some ideas and maybe plans to insert a lattice structure into your cavity system. And then also, what are the, secondly, this is another big question, is what are the ideas of scaling this up to a more many-body context?
Yeah, so that's great. In fact, they're in some ways related to each other. Matt, Lucas, and Claire have been very much hard at work on learning how to correct aberration in these optical cavities beyond the paraxial limit, beyond the limit of quadratic optics, and so forth. So at some level, either putting in aspheric mirrors or AR-coated very low loss lenses is going to allow us to make very, very large systems. We expect, 30 to 100 modes, depending on exactly how things turn out. So that could be Laughlin states up to like 10, 20, 30 particles. But along this journey, what we've discovered is that if you only need finesses up to 10 or 20,000, you can actually put a whole variety of interesting things into your cavities. So we're learning to put electro-optic modulators into these cavities. We're hoping to put to have the coating companies actually pattern the mirror substrates for us to produce lattice potentials. You can imagine using a silicon nitride membrane almost right up against one of the mirrors, but very slightly tilted, it turns out that will also produce a lattice for the photons. So I think there's a whole range of really wild stuff one can do while maintaining this very low loss limit that just hasn't been explored, because typically a finesse of 10,000 is not enough to enter the strongly interacting regime without this Rydberg blockade effect. And at a finesse of 100,000 or 1,000,000, there are many fewer things you can put in the cavity. Great question.
Yeah, thanks. Let me go to, I guess, a more general question that actually concerned the first part of your talk, and dreaming of how to make stronger photon-photon interactions. You emphasize that there's this problem between the low energy of the incident photons, and in the case of like electron pair production, the very high energy required to do that. So does that generally, this is a question from I Trong, should you generally be thinking about working with higher energy photons to begin with? Should we be developing a nonlinear optics experiment with X-rays or even gamma rays? Should we be making use of the X-ray portion of the atomic spectrum?
I think that's an awesome question. I've started to think about that a little bit myself, right? Like, I think it would be really wonderful to do X-ray multimode cavity QED or gamma ray multimode cavity QED. I think my understanding is that there's a challenge in making mirrors there. You know, we've gone down from finesses of hundreds of thousands or millions to finesses of a few thousand or tens of thousands. And I think one would have to look a little bit carefully at the numbers, perhaps quite seriously, to make sense of can you even get a finesse of 1 or 2 in one of these X-ray cavities. But I think if you could do it, it would be really, really interesting and cool.
Okay, well, thank you for everybody who is submitting questions. I'm sorry I could not all, but I want to be respectful of the time. Alicia, would you like to wrap up for us?
Yes, so I just wanted to thank John one more time for the wonderful talk, and I'm going to steal the screen share in order
I'm sorry. Yeah.
To advertise the upcoming talks. So we have the next week's virtual AMO seminar, which will be given by Holger Müller from the University of California in Berkeley. And we also wanted to advertise next Thursday is the European Quantum Science Seminar given by Jacqueline Bloch.
Great talk, John.
Thanks, Adam. So do we just sit here awkwardly now? Is that the plan?
No, I get to ask you a question. Okay.
Oh, wait, before you do that, since we're off the clock, Emmy's coming. Come on, Emmy, it's party time. Okay, what's your question, Adam?
Are there prospects for making compressible ground states by having a tunable coupling between the reservoir and the many-body system, so that you can like basically like make a mod insulator, turn off the reservoir coupling, and then ramp, you know, between two phases?
Super cool. My guess is that Brendan Saxberg is listening in right now. He has been working on the numerics for that over the past week or two.
Okay.
You know, during the epidemic, while we're all quarantined, everyone's a theorist. So so yeah, I think that stuff is really, really interesting. That's and I think you can potentially also do it with the optical photons, although it's certainly easier with the microwaves. So yeah, that is our next immediate next plan for that experiment.
Oh, okay.
If you didn't get a good look at Emmy the cat.
Does Emmy the cat mind being live on YouTube?
Oh, she's live on YouTube?
Cats are
The first cat on YouTube.
Yes, exactly, right?
Wow, we've really broken ground here, people.
Exactly.
Awesome. I guess
Now we just need minions.
John, how many photons do you get in your when you're trying to measure these G2 experiments and you run them all at once? How many photon pairs are you measuring?
That's a good question.
I think actually someone, I don't know, you might have, yeah, I think that was one of the questions.
That's Philip Price's question. I'm not.
Yeah, good question. So I think we operate at count rates of hundreds of hertz to kilohertz detected. But the good news is we can collect over 100 milliseconds of data per mott. And so, you know, when we're operating at the atom numbers where we get the very best performance, really, really high atom numbers, you know, it's like actual detected pairs is maybe a couple at most. But when we reduce the atom number to make, and the interactions are a little weaker, you know, it can be tens. But the data rates are low. I think at this point, largely because we don't have enough blue power, actually. So our so we're dominated by the line width of our polaritons rather than the decay of the cavity. I don't know if that made any sense to you, Dan, but you know, there's this dark state rotation angle story for the polaritons, and if they're too Rydberg-like, which is essential for having strong interactions, actually, then basically the collective state decays before the photon can leak out, and that's the main limitation on our data rate.
Yeah, right.
John, I was trying to understand how to think about, so at the end of the day, you come up with, you basically measure what the wave function is that you have. You tell us exactly what Laughlin state you're in. Presumably, you know, in the experiment, I guess it's not exactly, it's not a pure state exactly, right? But you have these correlation measurements. So do those prove entanglement, or like, how should I think about that?
I think the combination of the correlation measurements in angular momentum space and the anti-bunching in real space proves entanglement. So the way I would say it is, you're saying that there are two states you can have, right? One is two photons with angular momentum 1, and the other is a photon with angular momentum 0 and one with 2. So one thing you can do is measure the diagonal elements, and that's these angular momentum correlators. And then when you measure in real space, you measure the off diagonals. Is that?
Yeah, I think that helps. Yeah, cool. I have another question.
Yeah.
Don't mind. So, in principle, I guess you could drive, instead of like the 3 mode, you could drive some higher mode, like the 6 mode. And then I guess you could make pairs that have a higher difference in angular momentum. Like, would you sort of get a cascade? And I don't know, are those states interesting? Are they just complicated and a mess, or?
So this is actually a really cool thing. Let's imagine, let's forget about the 036 thing. Let's just go back to a normal Landau level, okay? If you drive on the L equals 0 mode of a normal Landau level, you get a 1 photon Laughlin state, right? It's 1 photon in the L equals 0 mode. If you drive on the L equals 1 mode, you can make a 2 photon Laughlin state, and you cannot inject 3 photons at all. If you drive on the L equals 2 mode, the first thing that you can generate is 1 photon in L equals 2, right? Then you can put 2 photons into L equals 2 and they can collide. And there are actually 2 different 2 photon states you can make, right? Either like 0, let's see, either 0, 4 with a little bit of 2, 2 to cancel out the amplitude, or 1, 3 with substantially more 2, 2 to cancel out the real space overlap. Yes? And then you can put a 3rd photon in, and that 3rd photon makes a 3 photon Laughlin state. So the question is, what are those 2 photon states that you got beforehand? Those are Laughlin states with 2 particles and 1 quasi-hole. Okay, and the quasi-hole is kind of like delocalized in space, but you've put 1 quasi-hole into the system. And so the way to think about that cascade, the system with a quasi-hole is still compressible, right? So you could imagine doing something if you add a potential bump that prevents photons from going into L equals 0. Then when you inject on L equals 2, you would make a 2 photon Laughlin state with a quasi-hole at the origin. Right? And so when people talk about trapping quasi-holes with like local potentials, that's kind of the set of ideas that they're talking about. And in fact, you wouldn't have to put the bump in the middle. You could imagine putting it anywhere and it would still stabilize a 2-photon Laughlin state just with the quasi-hole wherever you put the potential bump.
Mm-hmm.
Does that kind of make sense?
Yeah, cool.
For Monica's first question, I mean, I sort of wonder whether there are bounds actually that you could consider for, because I think, I mean, there are product states that would also have off diagonals in the density matrix for the 2-photon state, like any, like if I have 2 particles pointing along the x direction, I'm still going to have off diagonals in the 2-particle basis, and even some that I think would map onto sort of the kinds of things that you're measuring.
Okay, I think one has to be a little bit careful. The question really is, did we carefully measure how often we get, say, 2 photons with L equals 2 and 2 photons with L equals 0, right? Or 1 photon with L equals 0 and 1 photon with L equals 1, or 1 with L equals 1 and 1 with L equals 2, right? Because we haven't actually measured those carefully. But if you carefully measured those, the kinds of unentangled states that you're talking about would also have those pairs in them.
Yeah.
Does that make sense?
Yeah, no, I agree with that. Yeah.
The basic statement.
Kind of inequality you could write down based on those measurements to prove entanglement. Yeah.
Yes. So what I would say is, at some level, this experiment is somewhere between condensed matter and quantum optics, right? Like, I think you can certainly find holes that say this is not an entangled state, right? There's other stuff going on. But we measure physical signatures that, for example, the pairs aren't produced if you don't conserve energy, right? As you move those outer 2 states around, when the sum of 2 photons with L equals 1 doesn't equal L equals 0 plus L equals 2, you don't make the pairs anymore, right? And so on physical grounds, you can certainly make strong arguments that it should be the Laughlin state, but I do agree with you that somehow at the end of the day, what you really want is some kind of really good multimode correlator measurer object that can measure all of the off diagonal things and all of the on diagonal things, and nail it down. But it's not totally clear to me what that object looks like.
I think you're right. I mean, I think it's some combination of the measurements of the angular momentum the two photon angular momentum populations combined with the size of the interference dip, because that quantifies their coherence.
But I think there's maybe even a bigger thing to say, which is you can make that tomographic measurement for 2 particles. Imagine I tell you I've made a 10-photon Laughlin state. There's no way you're going to be, I mean, even if you have really high quantum efficiency, there's no way you're going to tomographically characterize that state. So at some point,
like because you actually have, how do I think about this? I'm wondering whether you can do some sort of homodyne or heterodyne measurement with the light that you're seeding into the cavity to actually look at whether you have certain phase relationships among the components in the angular momentum states.
It's an interesting thing. I think one answer to your question is,
oh no, you definitely could, right? Because as long as you could definitely make that kind of interferometer.
I see, but then you want to make a 2 intensity interferometer where each one is homodyned. Right, because remember the collision process conserves the sum of the 2 phases of those 2 photons, not their individual phases. So you can't measure the individual phases.
So you need to both filter on the components of the angular momentum that you want to interfere with, and then do the interference for each of those components. That's what you're saying?
And you have to correlate them on a shot-by-shot basis, because the components don't individually have well-defined phases. It's only their sum that has a well-defined phase.
But if you're beating it with the same local oscillator that seeds it, doesn't...
I guess my point is, if you look at either one individually, you will see no well-defined phase relationship.
No, that I understand. Okay.
I guess all I meant was you need to make sure that when you see a click in your L equals 6 homodyne, you also look for a click in your L equals 0 homodyne.
Okay.
You see what I'm saying,
no,
kind of?
no, I definitely do.
I definitely agree with you. You can do that for 2 photons, but I don't think you can do it for 3. Well, maybe you can. You say like, look, just do homodyne on each of them.
Yeah, I see what you're
Do a
saying.
3 photon coincidence in homodyne. That's hilarious. You're totally right. Okay.
What I
I
really
don't
wanna
know
see
if the rest of the group is
what I
still
really
logged
wanna
in, but if so, you should set it up now.